Hey guys, so we are on lesson 3.1 polynomials. So we're out of the arithmetic and geometric sequences portion of the unit. Now we're into polynomials. Polynomials are going to play a huge part in Math 3. Things are going to get a little bit harder from here, but don't let that discourage you. Just know that it's coming, and yeah, we're going to have to work hard at it, but that's okay. You made it to Math 3, so you guys can handle it, all right? So what we're going to do today is we are going to unpack our learning targets. This is our very first lesson from the Springboard book. Since we've started, we've been using other handouts from other resources. So you should have your books. If you don't, these PDFs are attached under the notes video. If you don't have your book, you need to go to the school and get your book. That way you won't have to print any of these. They'll just be there. They're perforated so you could tear them out, and they also have 3 holes in it so you can put it in a 3-ring binder. And I recommend doing that so that you can keep the notes in order. There's going to be some things that we skip, so you won't be needing everything out of that book. And some of the time I'll have my own handouts that I've made that I like better than using Springboard, just like what we started off with. So it's just easier if we keep it in order in a 3-ring binder. Okay, that's what I highly recommend you guys to do. Plus, it's a good skill to get you guys ready for college. All right, so to unpack the learning targets, we circle the verbs and underline what we're doing with those verbs. So for the first bullet point, it says, write a third-degree equation that represents a real-world situation. So we're going to write a third-degree equation that represents a real-world situation. We're going to graph a portion of this equation and evaluate the meaning of a relative maximum. So there's some terminology in there that's going to be a little bit different for you guys, but that's okay. It says the United States Postal Service will not accept rectangular packages if the perimeter of one end of the package plus the length of the package is greater than 130 inches. Consider a rectangular package with square ends as shown in the figure. So it's pretty much a box, but it's a rectangular box because it's lengthwise, okay? Normally, I would do this as a little group activity. You would work with your elbow partner, and you would fill in this table of values. We don't have that, obviously, so we're just going to do it together. So it says work with your group on this item and on items 2 through 5. Assume that the perimeter of one end of the package plus the length of the package equals the maximum 130 inches. I want to underline all that. It's telling us to assume some information here. Okay. So it says complete the table with some possible measurements for the length and width of the package, then find the corresponding volumes of each package. Okay. So what do we underline? It says to assume that the perimeters where we add up all the sides of one end of the package plus the length of the package equals a maximum of 130 inches. What does that mean? One end would be the square end, or it says plus the length of the package. So the length would be however long it is, okay? And it would equal a maximum of 130 inches. Okay, so I'm going to give you some possible values. So we have this table, width, length, and volume. Okay, it says right here on the drawing that these are our widths and this is our length. Okay, we have a square end and then the length of that package. So let's start with widths of 10, 15, 20, 25, and 30. Okay. Let's figure out what lengths we could have. Well, if I have a package that has ends that are all 10s, 10, 10, 10, 10, 10, 20, 30, 40, what could that length be? Well, remember, it's got to add up to 130. So 40 plus what equals 130? 40 plus 90 equals 130. So then the length must be 90 inches. Okay. I'll come to the volume last. For the next one, if it were 15 inches all the way around that end, what would be the length? So 15, 30, 45, 60. So that's 60. And so how much would be left over so that that could be the length? Well, 60 plus what equals 130? That will be 70. So 70 goes in that box. And then, well, what if the ends were 20? I'll put it up here. So 20, 20, 20, 20. So 20, 40, 60, 80. How much more do we need to add as the length so that it adds up to 130? Well, 80 plus what equals 130? Well, that is 50. 80 plus 50 equals 130. So 50 will go in the box. Okay. Following that same pattern for the other two, we'll have a length of 30 when the widths are 25, and we'll have a length of 10 when the widths are 30. Okay. So we can see as the widths are increasing in size, the lengths are decreasing in size. Now the volume of, this is basically a rectangular prism. The formula for volume of a rectangular prism is V for volume equals length times width times height. L times W times H. Length times width times height. Okay, so to find the volume, I'm going to need to multiply by length, width, and height. Well, the height of the box is also the same as the width. How tall the box is the same as the width. So I'm going to have 10 times 10 times 90. Well, 10 times 10 times 90 is 9,000. So 9,000 inches cubed. And then 15 times 15 times 70. Where'd my calculator go? 15 times 15 times 70 equals 15,750. And then 20 times 20 times 50 is 20,000. And then 25 times 25 times 30 is 18,750. And then I'll just give you the last one. It's 9,000. So it started up as 9,000, and then it increased, and then it decreased back to 9,000. So it went up, peaked, and then it went back down. Huh, interesting. Okay. All right, so now it says, give an estimate for the largest possible volume of an acceptable United States Postal Service rectangular package with square ends. Okay, so the largest possible on our table looks like it's this one. But notice how we only counted by fives, 10, 15, 20, 25, 30. We didn't do 21, 22, 23, 24, 25. We didn't see where it exactly peaked at. So it's actually going to be around 20 and have a volume of 20,000. So the volume is going to be around 20,000. I can't say it will be exactly 20,000 because I don't know where exactly it peaked. We didn't try 21, 22, 23, 24. Okay. So I'm going to say roughly around 20,000 inches cubed. Okay. All right. Turn the page. We are on page 32 now. Says, model with mathematics. Use the package described in item 1. Write an expression for L, the length of the package in terms of the width. The width of the square ends of the package. So, remember we had our picture. We had the end, which was all of our widths, and then the length. And remember that had to add up to what? 130 inches, right? So let's write an expression for that. So the length plus 1, 2, 3, 4 of the width, so 4 W's, equals 130. But we have to have an expression in terms of the length, or in terms of W. So in terms of W means we need to solve for the length. So that means I need to subtract 4W from both sides. And I'll get that L equals 130 minus 4W. And I'll box that. Always box your answers. Makes it easy for me to see when you've completed your work there for that problem. Letter B, write the volume of the package V as a function of W, the width of the square ends of the package. So let's remember on the last page we used the volume formula. Volume is length times width times height. Remember, width and height are the same thing because how tall the box is the same as the width, okay, because that's a square end. So for volume, we already have an expression for length. I could plug that in for L. So that'll be 130 minus 4W times W can be itself. But remember, H, the height is the same as W, so times W. Okay, so we're going to get, I'm going to go ahead and multiply W times W. W times W is W squared, so we'll have 130 minus 4W times W squared. And that is the formula for volume for this rectangular prism, for this box. Okay. All right, so it says in letter C, justify your answer by explaining what each part of your equation represents. As you justify your answer, speak clearly, blah, 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 blah. Remember to use complete sentences, blah, 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 blah. You know how to do all that, okay? Or we should. I hope you guys do. I'm going to assume that you do. If you don't, then it's a little bit of some English schooling over here. All right, so this is what I want you guys to write for your notes. I'm going to put W squared represents the area of the what? Well, area of a square is length times width, or a side times side. W times W is W squared. That's the area of the square end. Represents the area of the square end of the package. And then we also need to explain what the 130 minus 4W represents. So we can say 130 minus 4W represents, remember it stood for length, so it represents the length of, I'm going to squeeze in the package. So we're just describing what each part of that formula was, what it means, what is it tied to. All right, number 4, it says, consider the smallest and largest possible values for W that make sense for the function that you wrote in item 3B. Give the domain of the function as a model of the volume of the postal package. Express the domain as an inequality in interval notation and in set notation. I'm just going to use interval notation. We'll go over more on the notations a little bit later. You're really going to need to get a handle on that, but I'm just going to ease you into it. Okay. So what I want you to write is actually the so for number 4, we have to figure out, okay, well, which numbers work and which ones don't pretty much. So normally in class, we would graph this on Desmos and we would see where it peaks. And we would use that information to help us drive this answer. But we have to remember that this is a package, okay? So a package is going to have a length and a width. So the length and the width can't be 0. If one of those variables is 0, then the whole volume formula is 0. But a package can't have 0 volume. So we have to be careful about that, all right? So what we got to do is try to figure out, okay, well, what doesn't work then? What will make this 0? Well, obviously, if W is 0, then it wipes out the whole thing. So we know that W can't equal 0. That doesn't make sense. Another thing that doesn't make sense is 32.5. Watch this. 130 minus 4 times W. So if I have 130 minus, and I'll put this in parentheses, 4 times 32.5, guess what it's going to equal? 0. And then when I multiply by 32.5 squared, it won't matter. It's going to wipe it out and be 0. So W also cannot equal, 32.5. Okay. So those are two things that X cannot equal, because the volume of a package can't be 0. And these two values will make this function 0. So what we got to do is we have to figure out the domain. So that means our domain, I use a capital D for domain. I'm going to use interval notation, so maybe I'll underline that. We'll use interval notation. Since I can't include 0, I'm going to use a parentheses as my bracket, because the 0 will just be my boundary line. I can start from 0, that can be my frame of reference, but I can't equal 0. To equal 0, I would have to use the square bracket. So I can be on the domain from 0 to 32.5, but I can't equal 32.5, so I'm going to put parentheses. Okay. As an inequality, I'll go ahead and put what it would be as an inequality. I'll put it over here. As an inequality, it would be 0 less than X less than 32.5. So X would have to be, or in this case, W, I should put W. W would have to be the values from 0 to 32.5, but we can't equal 0, and we can't equal 32.5. Okay, so this would be our domain. Domain has to do with the X's, the X-axis. Okay. All right, so it says, sketch a graph of the function in item 3B over the domain that you found in item 4. Include the scale on each axis. Okay, so for our graph right here, this is what I want you guys to do. Let's label the X's. We'll count by 4s. So 4, 8, 12, 16, 20, 24, 28, 32. And this is the width. And then remember, the width is in inches. And then for the Y's are going to get really high up there, and we know it's going to peak around 20,000. So I'm probably going to want to count by thousands or 2,000s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Yeah, 2,000s are going to work. So 2,000, 4,000, 6,000, 8,000, 10,000, 12,000, 14,000, 16,000, 18,000, 20,000, 22,000. And this is the volume, and the volume is in inches cubed. Okay, so anytime we have to make a graph and it's tied to a particular situation, we got to make sure to label our graphs properly. Sorry, I need a drink of water. Okay. All right, so let's go ahead and graph some stuff on here. Okay, so we know a couple of things already from the previous page. From the previous page, we know that when the width is 10, so 10 would be between the 8 and the 12. When the width is 10, the volume was 9,000. So here's 10,000, so 9,000 would be right in the middle. We know when the width was 15, so right before the 16, that the volume was 15,750. So it's 14,000, so 15,750 we'll approximate it to be about right there. And then when the width is 20, the volume is 20,000. 20,000, that exact point. And then when the width is 25, here's 24, so a little bit after 24 will be 25. the volume was 18,750. So this is 18,000, so let's put it about right here. Okay, not exactly on the 24 though, because it was 25. And then at 30, so 30 will be about right here. It was back down to 9,000 again. Okay. So what we don't know is a value between 20 and 25. So let's try 22. So let's do a W and volume, and let's try a width of 22. So let's go ahead and plug it into our function. If we have a W that's 22, 130 minus 4 times 22. Let me just change that 32.5 to 22 times, actually, let's just figure out what that is. It's 42, and then times 22 squared is 20,328. Okay, so at 22, it's a little bit higher than 20,000. So as we can see, if I connect these dots, just to see what the shape is, look at what it looks like. It's not a perfect parabola, but it is pretty darn close to a parabola. It's making a curve. It's increasing, 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 and then it decreases. So it has a turning point, okay? So normally I would graph this in Desmos, and can I think I can. So I went to Desmos, and I'm going to go ahead and plug this in. Now, when you type this into Desmos, Desmos only uses X's and Y's. So your X's are the W's in our function. And so if I type that in, it'll be Y equals 130 minus 4X times X, and I got to raise it to the second power, X squared. What am I missing? No, it's not going to work this way. We need to simplify that out. So when we multiply out the W squared times 130 minus 4W, but with X's, you'll get 130 X squared minus 4X cubed. Oh, it was right. I just need to zoom out. So Desmos is just kind of picky about the screen. So let me change my grid. I don't need any negative X values because the width can't be negative. So I'm going to go from 0 to, I know that my domain is 32.5. Okay. I don't need any negatives on my y-axis because the volume being negative doesn't make sense. So we'll go from 0 to, we know it's at 20,000. Let's go to 22,000 and see what happens. Ah, there it goes. There we go. There's our picture. Let me zoom out a little bit. Okay, so it's a cubic function, a cubic polynomial on that graph. But we only need like from here to here because it doesn't make sense for width to be negative and it doesn't make sense for volume to be negative. So I only need that part, okay? So from that graph, I can see where the zeros are of my graph. Okay, and those zeros are right here, 0, 0. So when X is 0, Y is 0, which makes sense. If X is 0, it wipes out the whole thing. So we can write that down. And then my other 0 is right here at 32.50, exactly. So, but we know that when we plug in 32.5 for X, it wipes out the whole thing. It makes it 0. And that point doesn't make sense either because you can't have a volume that's 0. Can't have a volume that's 0, can't have a width that's 0. So those are the two. So for number 6, if we go back to our papers, it said use a graphing calculator to find the X coordinates where Y equals 0, the X intercepts for the function that we graphed. So those X intercepts are X equals 0 and X equals 32.5. Okay. Then it says use a graphing calculator to find the coordinates of the maximum point of the function that you graphed in item 5. Okay, so I'm going to switch the camera back over here. We need to find the maximum point. The maximum point is the highest point this little curve is going to reach. And that's it right there. So the highest it's going to reach is that exact point. So go ahead and write that down for number 7. I'll make sure not to move it from this screen so you guys can write it down. So we're writing down the coordinate 21.667, comma, 20,342.593. Okay, so I'm going to move it back over. Okay, so it says in number 8, what information do the coordinates of the maximum point of the function found in item 7 provide with respect to an acceptable United States Postal Service package with square ends? So what does this maximum point tell us? Well, it basically tells us the max possible volume of the package. So we can say the max possible volume of the package is 20,342.593 inches cubed when the width is 21.667 inches. And that's what that means. Okay, for the check your understanding, let's just go over those really quickly. It says explain why the function v of w that you use in this lesson is a third degree equation. Well, we're dealing with volume. Volume is length times width times height. So we're dealing with 3 dimensions. So let's also point out when we have our v of w function, it was 130 minus 4w times w squared. Remember, I had to multiply this out in order to put it into Desmos. We get 130 w squared minus 4 w cubed. So there's our cubic right there. It's third degree. So this tells us that it's cubic, that it's to the third degree, that it's 3-dimensional. Okay. Explain why the value of w cannot equal 0 in the situation. Well, w stands for the width. Width doesn't make sense to equal 0. So let's put width can't equal 0. That doesn't make sense. Okay. All right, number 11, it says explain why the value of w must be strictly less than 32.5 in this situation. The reason why it has to be strictly less than 32.5 is if it equals 32.5, then the volume will be 0. And that doesn't make sense. But everything less than that number will work so that the volume won't be 0. As long as the volume isn't 0, it's okay. In this situation, is it possible for the range of the function to be all real numbers? Why or why not? So the range has to do with the y values. Y values are along our y-axis. So remember our function, our graph. These y values. So it doesn't make sense to use the whole number line, the negatives also, and 0, because you can't have a 0 volume and we can't have a negative volume. That makes absolutely no sense. So we can only use the positive side of the y-axis. So that means we're not going to say the range is all real numbers, because all real numbers says positives, 0, and negatives. We only want just positive values for the volume. So our answer for that will be in this situation, is possible? No, because volume can't be 0 or negative. Those values don't make sense. Number 13, it says another method of shipping at the post office allows for the perimeter of one end of a box plus the length of that box to be no greater than 165 inches. Serena wants to ship a box whose height is twice the width using this method. She says the formula for the volume of such a box is V of W equals 165 minus 6W in parentheses times 2W squared. Her sister Monique says the formula is V of W equals 165 minus W times W squared. Who is right? Justify your response. Well, Serena was saying that she wants it to be twice the width. These numbers twice the width means that you're multiplying the width by 2. Now, Monique, her formula doesn't show multiplying the width by 2, but Serena's does. It has a 2W squared. So who is right? Serena. Okay. And that is because if we are increasing the width to twice the width, and our heights, which are W, stay the same, and then we have our length, the perimeter is going to be 2W plus 2W plus W plus W is 6W. Okay. So we'll have V of W equals, what did it say? 165 is the total minus 6W. That's going to represent our length. And then times the width will be 2W squared. Okay. All right. So that is, oh, you guys can't see. So that is the formula for that. Turn the page. And then we're on that last page there. This is where your homework is going to be. So you're going to be doing, this is part of it. This is only the first half of the lesson. So your assignment is to do numbers 14 through 18. This is part of it. The other part will be 3.2. All right, I'm going to try to move through this pretty quick for you guys. This is the second half. All right, so for this one, we're going to be sketching the graphs of cubic functions, just like we saw in 3.1. We're going to identify the end behavior of polynomial functions. Now, as you go higher up in math, end behavior becomes more and more important, okay? In fact, if you are planning on maybe moving up to calculus, end behavior is huge in calculus, okay? So it says, when using a function to model a given situation, such as the acceptable United States Postal Service package, the reasonable domain may be only a portion of the domain of real numbers. And we saw that in the last lesson. Remember, the portion of real numbers that we could use was from 0 to 32.5, because between those two numbers, the ones in the middle made sense, okay? Moving beyond the specific situation, you can examine the polynomial function across the domain of real numbers. So a polynomial function in one variable is a function that can be written in the form like this. I know that just looks like a bunch of mumbo jumbo, but basically it means from highest degree down to lowest degree. So let's go ahead and look at what standard form is. Standard form, like I just said, is how you always will write polynomials. They always need to be from highest degree to lowest degree from here on out, okay? So, for instance, we have our leading coefficient. The leading coefficient is the number in front of the highest degree term. The highest degree in this polynomial is the 5th degree, so there's our leading coefficient. The degree of the polynomial has to do with the highest degree of the polynomial. So the highest degree is this 5. So this is a 5th degree polynomial. Okay. And where are all my highlighters? Then we also have the 2x squared there. It's just a term. Okay. It's somewhere in between the beginning and the end. All right. And then we have the constant. The constant is always the number on the end. Okay, it's always just a constant, always just a number. No variables next to it. Okay. Also, we have a 0 of a function is a value of x where the function f of x equals 0. A 0 of a polynomial function is a solution of the polynomial equation. So zeros, roots, x-intercepts, those are all considered zeros of the function, okay, and solutions. This means the number n is a 0 of a polynomial function f of x if and only if f of n equals 0. If n is a 0 of a polynomial function, then x minus n is a factor of the polynomial function, and we'll talk about that a little bit later. So here are some attributes of a polynomial, of the graph of a polynomial. So, for example, we have an attribute, the constant term is the y-intercept of the graph. So that means if I were to graph 7x to the 5th plus 2x squared minus 3, that means it's going to cross through the y-axis at negative 3. So whatever it's doing, I don't know what this polynomial looks like. It's crossing through the y-axis at negative 3. Okay. Next, the degree tells the maximum number of x-intercepts or zeros the graph of the polynomial can have. So this one is a 5th degree polynomial. So it could have a maximum of 5 zeros. Now it could have 1 0, it could have 3 zeros, it could have 5. 5 is just the max that it could have. Okay. The degree of the polynomial gives you information about the shape of the graph at its ends. So the degree is going to tell us its end behavior, and we'll talk about that in a little bit too. So the degree is an important thing. If it's an even degree versus an odd degree is what we're going to focus on. And last but not least, the zeros of a function are the x-intercepts of the graph. Zeros are also called the solutions. They're also called the roots. Wherever they cross the x-axis, those are the zeros. Those are the x-intercepts. Okay, so there's a lot of terminology there, and there's just some things that you have to know. Over to the right under math terms, there's some other terminologies, like when the degree is 0, the constant would be considered 0 degree because that's technically negative 3x to the 0 power. You learned that in math too. Linear is when the degree is 1. It's a quadratic, a parabola, when it's a degree 2. It's a cubic when the degree is 3. It's a quartic when the degree is 4. A quintic when it's the degree 5. And then after that, I don't remember. I don't know. They start getting weird. They start sounding weird. We usually don't go higher. I mean, you'll see higher than a quartic, but we don't usually name it higher than a quartic. Okay, next page. All right. Oh, I'm having trouble turning. Okay. It says write a polynomial function f of x defined over the set of real numbers in standard form, so highest degree down to lowest degree, such that it has the same function rule as v of w from the previous lesson. Okay, so from the previous lesson, we had, I'll write it over here, v of w equals, we had 130 minus 4w times w squared. Okay, so, but we want to change it to an f of x. So we're going to rewrite that. We're going to change all the w's to x's. So I'm going to call it f of x equals 130x minus 4x times x squared. I'm going to distribute that x squared, and we'll get 130x squared minus 4x cubed. Then we got to put it in standard form, so we have to put the highest degree first, which is the negative 4x cubed. And then since the 130x squared is positive, it's plus 130x squared. And let's rewrite that. That is f of x. There we go. All right, and we're going to graph this. So we're going to not use Desmos. We're not going to cheat using that. We're going to use a good old-fashioned t-chart. Okay. Now, here are some things that we know about this graph. We know that it's going to hit the x-axis at 32.5 because that makes the volume 0. Okay, so we already know that it's 0 at 32.5. We also know that from our table from yesterday, that when the width is 20, the volume was exactly 20,000. Okay. And we also know that when the width is 0, the volume is 0, the 0.00. But now, since we have the negative sides of the graph, let's plug in some negatives. So let's try a negative 20. Let's try a negative 32.5, and then we'll go from there. Okay? So if I plug in a negative 20 for x, I'm going to have negative 4 times negative 20 cubed. Well, negative 20 times negative 20 times negative 20 is still going to be a negative. So let's type parentheses, negative 20 raised to the third power equals negative 8,000 times negative 4. What's a negative times a negative? Positive 32,000, and then plus, I'll put 130, and then our x is negative 20 squared. Well, negative 20 times negative 20 is a positive 400. So wait, it should be plus, oh no, yeah, times 400, sorry. So 84,000. That's huge. So when it's negative 20, that's way off my graph. I won't even be able to graph that. So let's look at the negative 32.5. So basically, I'm going to do, blah, blah, blah. Whenever I plug it in, this is what you're going to get. 274,625. 274,625 is what you'll get when you plug in negative 32.5. And let's plot these and see what we get. See what it starts looking like. Okay. So if I have 0, 32.5, so this one would probably be about 35. So 32.5 will be approximately right here. And then 20,000. And then 0, 0. And then negative 20, 84,000's way off my graph. Negative 32.5, 274,000, way off my graph. So I need to see what's going on over here. Remember when we looked at it on Desmos, we know that there is something that goes on over here. So let's try a smaller negative, something closer to 0, so technically a bigger number. Let's try a negative 10. When you plug in a negative 10, you're going to end up getting 17,000. So negative 10 and 17,000 would be approximately right here. Okay, so the shape of the graph approximately looks like this. And cubics look like that. Okay, so there's a couple of different things going on here. So we'll look at number 2. It says name any relative maximum and relative minimum values of the function. So a relative max is the approximate max of the function, and the relative min is the approximate min. Now we can't have an exact max or min because this arrow means that this function is going up to infinity, and this arrow means that the function is going down to negative infinity. So there isn't a max or a min per se, but in the middle we have these humps, and that's where the relative max and min are. So on this hump, what do you think that one would be? Yep, that's going to be your relative max. At this point, at that hump, what do you think that'll be? Yep, that's going to be your min, your relative min. Okay. So the relative minimum is 0, and the relative maximum is about 20,000. So we can say the relative minimum is 0. I'm abbreviating relative. The relative maximum is approximately, so the wavy equal sign, 20,000. Because we know it goes higher than 20,000 before it peaks over. So we're just going to say approximately, roughly 20,000. All right. So number 4, it says use a graphing calculator to sketch a graph of the cubic function f of x equals 2x cubed minus 5x squared minus 4x plus 12. Okay, so I have it ready to go on Desmos for you guys. So I typed in that function, y equals 2x cubed minus 5x squared minus 4x plus 12, and there it is. And we just need to sketch that in our graph, okay? So that's what it should look like. So we're gonna go to that graph. I do wanna point out some particular features though. Remember how we said that the y-intercept is the constant? So we know that this graph is going to pass through 12 on the y, okay? And it does on that graph that's in Desmos. The vertex is a little bit higher. It's at negative 0.333, 12.704. So approximately negative 0.3 up to 12.704. So just a little bit higher than that last point. Okay. And then it hits the y-axis, or the x-axis. It has a 0 at the 0.20. And it does this. It hits that point, and then it bounces back up. And then on the other side, it hits an x-intercept at negative 1.50. So here's negative 1, so 1.5 would be about right here. So this comes down to infinity. So it should look like that. And that's a cubic function. Okay. Now, if you ever need help figuring out Desmos, just let me know. We can work on that in a Zoom. I can help you. It'd be better to do that one-on-one instead of through a video. So, oops, I don't need that. Okay. All right, let's turn the page. All right, number 5. It says, name any relative maximum values and relative minimum values of the function f of x in item 4. So, the relative max would be up here. So let's mark that. That's our relative max. The relative min would be at this hump down here. So the upper hump, lower hump. And that maximum value was what, 12.7? And this minimum value was 0. Okay? So when we say what that is, we'll say the relative max was 12.7. The relative min was 0. Name any x or y intercepts of the function in item 4. It had 2 x-intercepts. So the x int for x-intercepts will be, there was one at negative 1.5, and there was another one at 2, comma. There was also a y int for intercept. And remember, that was the constant of the function, and that was at a y value of 12. All right. Check your understanding. It says number 7, decide if the function f of x is a polynomial. If it is, write the function in standard form and then state the degree and the leading coefficient. Okay, so this is completely out of order. So let's rewrite it in standard form, and then we'll be able to tell if it's a polynomial or not. So the highest degree is the negative 4x cubed. And then next would go the positive x squared. And then next would go the 7x, which is positive. And then the constant is negative 2. Well, that looks like a polynomial to me. There isn't anything weird going on in the exponents. There's no radicals. There isn't anything funky going on. So this is a polynomial. So I'm going to put over here, yes, it's a polynomial. And we put it in standard form, so check that off. And what's the degree? The degree is to the 3rd power. So this is a degree 3. Or you could say 3rd degree. And the leading coefficient is a negative 4. That's the number in front of that leading degree term. Okay. Number 8, it says, explain why f of x equals 2x plus 5 minus 1 over x is not a polynomial. Well, guys, take a wild stab in the dark here and guess what is the one thing that is preventing this function from being a polynomial. Can you see what it is? That. Yup, the fraction. The fraction is making it not a polynomial. It's going to do some funky stuff to the graph. Okay, so all I want you to know is that's what looks weird. That's not a polynomial. Okay? All right, number 9. We're not going to do number 9 because I don't want to use a graphing calculator, so we're not going to do number 10. We could do that later. And we'll skip 11. Okay, so on to the next part, end behavior. The end behavior of the graph is the appearance of the graph on the extreme right and left ends of the x-axis. That is, you look to see what happens to y as x approaches negative infinity and positive infinity. Okay, So when we write this, we're going to be writing things like as x approaches negative infinity, y approaches infinity. And as x approaches infinity, y approaches negative infinity. So we're going to write stuff like that. Okay, that's that notation. Okay, so it says examine your graph from number 4. Describe the end behavior of the graph in words and by using arrow notation. So I want to skip the whole wording part. Let's just use the arrow notation since that'll be the quickest way to write that. So I don't want these to be too long. So here's our graph from number 4. Look at the left end. So as x is going to the left, so that's going to negative infinity, what's the y doing? Y is approaching, that arrow means going down to negative infinity. So I can say as x approaches negative infinity, comma, y approaches negative infinity. And the other end is going towards the right. So that means we're going down the x-axis towards the right, so we're going towards positive infinity. What's the y doing on the graph? It's going up, 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 up to positive infinity on the y. So positive, positive. So I can say as x approaches positive infinity, y approaches positive infinity. And that would be how we write that up. It's super easy. I know it looks funky because that notation is brand spanking new to you, but it's okay. You're going to do it. It'll be fine. All right, number 13, it says examine the end behavior of f of x equals 3x squared minus 6. As x goes to infinity, what behavior does the function have? Okay, so we need to see what that's going to look like. So this is a parabola, and we can actually graph it pretty quick here. It doesn't have to be exact. We're going down 6, so I'm going to make sure I have room. So the parent function always starts at 0, 0, right? Well, this parabola has been shifted down 6 from the parent function. 1, 2, 3, 4, 5, 6. You learned that in math too. And the number in the front, that's what I use as the slope. So up 1, 2, 3 over 1 in both directions. So this is my parabola. Am I on number 13? Yeah, I'm on number 13. I'm like, what's happening here? Okay, so we're looking at the end behavior. As x goes to positive infinity, so we're going to positive infinity, so it means we're going to the right, because this would be towards positive infinity. What behavior does the function have? Well, that end of the graph is going up, 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 up as x is getting bigger and bigger and bigger. So it's going up towards positive infinity. So as x goes to positive infinity, y goes to positive infinity. Okay. And then how is the function behaving as x approaches negative infinity? Well, as x is approaching negative infinity, so it's going towards the left, the y values are going up, 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 up towards positive infinity. So y is going towards positive infinity. Okay, so it is possible to determine the end behavior of a polynomial's graph simply by looking at the degree of the polynomial and the sign of the leading coefficient. I want you to highlight that whole thing. It is possible to determine the end behavior of a polynomial's graph simply by looking at the degree of the polynomial and the sign of the leading coefficient. So I'm also going to even take this a step further, and I'm going to be like, let's circle the word degree and the word sign. So that means plus or minus, and the degree is like first degree, second degree, third degree, fourth degree, so on and so forth. Okay? So it says to use a graphing calculator to examine the end behavior of the polynomial functions in general. Sketch each given function on the axes below. I'm not going to use a graphing calculator for this. I'm just going to give you what they are because I don't want this video to be forever long. Okay, y equals x squared. This is the parent function parabola. Okay, Y equals negative x squared, it's just the same thing, but facing down. The negative makes it face down. Y equals x cubed, this is the parent function for a cubic. So it goes down like this, up like this. And then y equals negative x cubed is the same thing, but it gets reflected, so it goes the other way. Okay. Y equals x to the fourth, it actually is just a wider parabola pretty much. And x to the negative fourth, same type of thing. All right. And then y equals x to the fifth, it just makes a skinnier cubic looking, even though it's to the fifth. And then negative fifth means it's just going the other way. Okay. And here's a little cheat sheet that I give to all my students ever since I've taught Algebra 2, because it even helped them so when they were learning end behavior. So we have even versus odd. And let's make a table. And we're going to need positive versus, you guessed it, negative. Okay. So when it's an even degree, look at all these even degrees. Both ends are either facing up if they're positive. So positive x squared, positive x to the fourth, both ends are facing up. So no matter what it is, even if it's x to the 20th power, we don't know what's going to happen in the middle. But we know that the ends are going to be just like a parabola if it's an even degree. So that means it's going to go up to infinity, positive infinity on both ends. Okay. If it's negative, so if we look at negative x squared, negative x to the fourth, negative x to the sixth, negative x to the 20th, it's going to be facing down. So there might be some stuff going on in the middle, but at least the ends will both be facing down if it's an even degree function. So it might have some other stuff going on in the middle, like I said, but no matter what, if it's a even degree, but it's negative, it's going to be facing down. So that means it's going to go to negative infinity on the left and the right of the graph. So as x approaches negative infinity and as x approaches positive infinity, the y values will both go to negative infinity. For odd functions like x to the third and x to the fifth, notice how their end behaviors are exactly the same, even though the shapes of their graph are similar but a little bit different. This one's a little bit wider and this one's a little bit skinnier. It doesn't matter, their end behaviors are the same. But look at when they're negative, there's a negative out front. It just switches, it reverses it. Okay? So the end behavior changes to the opposite when it's negative. So when it's an odd degree function and it's positive, its end behavior will always look like this, where it's going to negative infinity as x approaches negative infinity, but it goes to positive infinity as x approaches positive infinity. If it's negative, it reverses the order. So as x approaches negative infinity, the y will approach positive infinity. And as x approaches positive infinity, the y will approach negative infinity. So it does the opposite. All right, turn the page. So number 15, it says, which of the functions in item 14 have the same end behavior on the right side of the graph as on the left side? So both ends facing up or both ends facing down. And that was the functions, all the even ones. Y equals x squared, y equals negative x squared, y equals x to the fourth, and y equals negative x to the fourth. What is true about the degree of each of the functions you identified in item 15? The degree of each of these is even. Make a conjecture about how the degree affects the end behavior of polynomial functions. So, even degree functions will have the same end behaviors. So both ends will face the same direction. Okay. All right. Number 18. For which of the functions that you identified in item 15 does the end behavior decrease without bound on both sides of the graph? We took care of that already. We talked about all four of them, so we're going to skip 18 and 19. Okay, and we'll go ahead and skip 20. Just because we're pressed for time. Turn the page. I do want to do number 25 a little bit because I'm pretty sure your homework is going to have some of that stuff in there. So let's go ahead and do one of these from number 25. It says use a graphing calculator to make a sketch of each given function on the axes below. So let's do B and C. Let's do those two. So I decided to do all four. So I got them all ready for you guys. So this one is the first one, letter A. So this is what it looks like, which makes sense because it's a cubic. It has an x to the third power as the highest degree. So we know that that's what it should look like. So let's go ahead and plot that on our graph. So on this graph, we're going to have a point at, or a 0 at -2, 0. So I have a point there. And then also Desmos is showing me that there is a peak after that at -1.5, 0.9. So -1.5, 0.9. So approximately right there, I'm going to guesstimate it to be. And then there's a y-intercept at -4 because it has a constant of -4. And then we have another 0 at 2, 0. And then there was also a point right here to make this hump, and that point is the point approximately 0.9, -6. So 0.9, -6, about right here. So this graph curves, oh wait, there's another 0. -1, 0. So right here. So this graph curves down like this, and then it loop, loop, loop. Okay. And I want to point out how many times it crosses the x-axis at. It crosses 1, 2, 3. Hey! It's an x cubed. Okay. For letter B, that's the x to the fourth function. So that is, let's get rid of that one, and it's this one. Looks like a W. Okay. So let's graph that one. That's part B. Sorry if I moved that really fast. I hope I'm not giving you guys a headache. All right, so I have a couple main points here. It crosses the x-axis at -3, 0. And then there's a peak, a minimum at -2.5, -4.9, -2.5, -4.9. So I'm going to say about right here. And then there's another 0 at -2, 0. Okay. And then the max, relative maximum, is -0.4, 20. So -0.4 be about right here, and then 20, so about up here, we'll say. And then it hits the y-axis at 0.18, so we'll pretend that that's 18. I didn't go up high enough. Oh well. And then we have a point at 1, 0, and then a point at 3, 0, and then there's another relative min at 2.2, -20. So 2.2, -20, about right here. So we know it's making a W-looking shape. There we go. Okay. Looks funky. All right, let's identify where the x-intercepts are. Crosses the x-axis 1, 2, 3, 4 times. Hey, it's an x to the fourth. You guys catching my drift? You catching it? All right, let's go back to Desmos. Letter C, I already have. It is the x to the fifth one. So let's x out that one and put this one up on here. Whoa, that one looks funky. Crazy funky. Okay, So on our graph, let's take that back. We have a 0 at -2, 0. And then we have a relative minimum at -1.4, -1.2. So -1.4, -1.2, about right here. And then we have another 0 at -1, 0. So it does this little loop, loop, loop. And then it kind of comes down like that. Okay. And then it has a y-intercept at 8. So I know it's going to come up here through 8. Okay. And then it comes back down and it hits the x-axis at 1, 0. So I know it's doing loop, loop, loop. Oh, I didn't mean to make that little squiggle. Oh, well. And then it goes below the x-axis at 1.6, -8. So about right here. And then it comes back up to the x-axis at the 0.20. Okay, they're not going to be perfect. It's just a little sketch. So don't expect to make these perfect. It's kind of impossible. All right, letter D. Oh, whoops, I forgot something. Sorry. We have 1, 2, 3, 4. 1, 2, 3, 4 x-intercepts. Yeah, it's an x to the 5th, but remember, it can have a maximum of 5 zeros depending on the degree. This one has 4. So it has 4 out of the max 5. Okay, next one is D, the x squared minus x minus 12. Uh-oh, focus, there we go. So I'm gonna click off that one, click on that one. That one we should know. The degree is a 2, it's a parabola. So all I really care about are the zeros, right there and right there, the y-intercept, and then the vertex. Okay, so let's go ahead and graph that. All right, so we have a vertex at 0.5, -12.25. So 0.5, -12.25 will approximate it to be right there. The y-intercept is the constant, so it's going to pass through -12. I have a 0 on the left at -3, 0. I have a 0 on the right at 4, 0. There's our parabola. I know mine sucks, but it's okay. It's okay, it's okay. All right. So on the next page, it's going to ask us some questions about that. So let's make sure that we can still see those graphs. So I'm going to have them right next to it. Sorry, I had to charge my phone because it was like out of battery. Because now I use it for everything. How many zeros does each function in number 25 have? Well, there was function A, B, C, and D. How many zeros did function A have? We highlighted them, 1, 2, 3. How many zeros does function B have? 1, 2, 3, 4. C has 1, 2, 3, 4. And D has 1, 2. I didn't mark those, but those are easy. It's a parabola. All right, use the graphs in number 25 and the number of zeros in number 26 to speculate about the relationship between the number of times a polynomial function touches the x-axis and the number of zeros of the function. So I'm not going to have you write anything down, but basically the number of times a polynomial function touches the x-axis could be less than or equal to the number of zeros of the function, because we saw that it wasn't exactly, like this one had exactly 3 and its degree was 3. This one is the degree 4 and it had exactly 4 zeros. This one is a degree 5, but it had 4 zeros. So it could be less than or equal to that highest degree. Okay? But we won't write that. Number 28, it says explain why the number of times a polynomial function touches the x-axis is not always equal to the number of zeros of the function. So the reason why it is that way is that a function could have duplicate factors, and there's only 1 0 for each of the duplicate factors. So for example, a parabola could cross through the x-axis only one time, right? And that's because what if we had a parabola that when we factor it was x minus 2 times x minus 2? That's 2 of the same factor. So it could possibly, that only counts as 1 0 because you go through the positive 2 only one way. Okay, and it only crosses through that same point once. You can't cross through it twice, it's just once. So that's what they mean by there could be a duplicate zero. Excuse me. Number 29, what are the zeros of each function in item 25? We won't list all the zeros and what they are. We already graphed all of them. What are the factors of each function? I do want to go over that. So let's go ahead and find the zeros for, let's do letter B. So the zeros for letter B, I'll just give them to you, were -3, -2, 1, and 3. So how would we write what the factors of each of those are? Well, if -3 is the 0, then before we solve, that means it was x plus 3. Because if you take x plus 3 and you set it equal to 0 to find a 0, you subtract 3 from both sides, and x equals -3. Okay? So we're basically just working backwards. So then the next one, if the 0 is -2, then the factor would be x plus 2. And if the 0 is 1, then the factor would be x minus 1. And if the 0 were 3, then the factor would be x minus 3. Okay, that's how you work backwards. That's a skill you're going to need this semester. Okay, turn the page. Examine each graph. How many zeros does each function have? Okay. This one has how many? 3. What about this one? 1, 2, 3, 4. Okay. So we can tell that the end behaviors are different. They're going in opposite directions. This one is going to positive infinity as x approaches positive infinity. And on this side, as x goes to negative infinity, this one's going to negative infinity. Same thing here. So the end behaviors are the same, so that means that these must be odd degrees. Now, because this one has more stuff going on in the middle, this is probably a degree 5 or degree 7 polynomial. This one's probably a degree 3. It's just stretched out a little bit. Okay, let's try the check your understanding. Number 32, I'm so sorry, this is a long lesson. It says, examine the graph. How many zeros does the function have? 1, 2, 3. What are the zeros of the function? Okay, we have a 0 at -3, -1, and +2. What are the factors of the function in number 32? Okay, let's work backwards. The factors would be a factor of x plus 3 to equal -3, a factor of x plus 1, and a factor of x minus 2. Number 35, explain how to write a possible function for the graph in 32. Then write a possible function. So what we can do to find a possible function that would match this graph would be to multiply the factors together. So I would multiply x plus 3 times x plus 1 times x minus 2. And now we need to actually do it, okay? So when you're multiplying 3 things, focus on 2 at a time. Everyone say that with me, 2 at a time. So I'm just going to work on the first 2 because they're the first 2. It's easy to focus on those. And multiply it out. X times x is x squared. X times 1 is x. 3 times x is 3x. 3 times 1 is 3. I can combine like terms, and I'll have x squared plus 4x plus 3. Put the parentheses back around it, and bring down the last factor. Because now we got to multiply that in. It freaks me out when the smaller factor is on the right. I like having the smaller factor on the left. So I'm going to do a little switcheroo. But it doesn't matter because 3 times 5 is the same as 5 times 3. It's still going to equal 15. So you can reorder when you're multiplying. It won't change the outcome. Just for me, it makes it so that I'll get it correct. All right, so x times x squared is x cubed. X times 4x is a 4x squared. X times 3 is a 3x. Now the inside terms. Negative 2 times x squared is a negative 2x squared. Negative 2 times 4x is a negative 8x. And negative 2 times 3 is a negative 6. Notice how I stacked like terms together so they're already grouped. X cubed had nothing to combine with. Negative 4x squared, or sorry, that's not negative. Positive 4x squared minus 2x squared is 2x squared. And 3x minus 8x is negative 5x, and then minus 6. So the possible function, let's throw a y equals in front, would be y equals x cubed plus 2x squared minus 5x minus 6. And we just came up with a possible function. How about them apples? All right. And then we're on this last page, and this is where the other part of your homework is. So this is the last part of it. You're going to be doing numbers 36 through 41. Okay. So when it says to sketch a graph, you can totally use Desmos for that. You just have to type in, instead of f of x, make sure you put y, because there's no f of x button in Desmos. Put y equals this. And then you might have to mess with the settings on the axes to make sure that you can see the graph in your window. If you need help with that, just let me know. We can go on a Zoom together and we can figure that out. Okay. You're going to name the x and y intercepts, relative max and mins. You're going to look for the factors of the function. You find the factors by looking for the x intercepts, the zeros. You're going to sketch a graph of any third degree polynomial function that has 3 distinct x-intercepts, a relative minimum at negative 6, negative 4, and a relative maximum at 3, 5. So answers can vary on number 39. You just have to make your own sketch of a third degree polynomial that has those conditions. Then you're going to decide if each of these polynomials is a polynomial function. If it is, write it in standard form and then state the degree and the leading coefficient. Okay, and then the last one, you're going to describe the end behavior of each function. So this is where you look at the degrees. So you're looking for the highest degree. So this is a degree 6. That's an even number. What does that mean for the end behavior? The highest degree here is to the 3rd power. So it's a cubic. What does that mean for the end behavior of this graph? You don't need to see a picture of the graph to tell what the end behavior is. You already learned what even and odd are going to show you. This is a positive even. This one's a negative odd. So that's it. Have a good day.